Alright, this is the lesson 4.4 supplement in the Calculus BC course, and if you're doing the AB course, it's the 6.8 supplement. So recall examples 1 through 5 in section 4.4 for the BC group and section 6.7 for the AB group, where you were asked to actually find area under the graph using these things called Reimann sums. Well, let me explain to you this topic just a little bit more. So, given that you have a function y equals f of x, I'm going to draw that over here. Whee! And your x interval goes from a to b. I want you to find the area below it using the rectangle approximation method with n rectangles. But here's the catch now. The width of the rectangles may vary, so they don't necessarily always have to be the same width. So the subintervals do not have to be the same width. And also the heights of each rectangle may vary as well. Okay? I'll say may vary. So to draw that out for you, like for instance, our first interval could be this long. And maybe this time I'll use the left height. So there's my rectangle. My second interval, perhaps, is this wide. And this time I'm going to use the right endpoint. Right? And perhaps my third interval could be this tiny. And I'm going to use the midpoint. So you see how they can vary. They don't always have to be the same. Now, when these changes are made, then you are really doing a general Reimann sum. RAM is what I call the rectangle approximation method. Those are the ones we did in those examples. Are just special cases of the Reimann sum. But really, a true Reimann sum says your height and width can be anything. Okay? There's no fixed things that need to happen. So if you think about what we're required to do now, the Reimann sum of the first rectangle here, notice it's delta x sub 1. That would represent the width. Okay, the delta x part is always the width of the first rectangle. And then f of c sub 1. Now c is just some x value that we chose in that region. In my example in the drawing, the c value would be the same thing as a because I'm using the left endpoint. But whatever you choose, this just represents the height of the first rectangle. Okay? And so on and so forth. F of c sub 2 is the height that you use for the second rectangle. In my example, that would be the right endpoint. Delta x sub 2 would just be that width in blue, and so on. You just keep adding them up, adding them up. And if you add up a whole bunch, it's really hard to write really compactly unless you use this summation notation. So this summation notation really just says find the sum of all of the heights multiplied by each of the widths. So all the rectangles that you've created. This k equals to 1 to n is the counter. So k equals 1 would be the first rectangle, k equals to 2 would be the second rectangle, all the way up to the nth rectangle in your picture. Key thing here once again, the Reimann sum height and width of the rectangles may vary. Okay. Now, you might be thinking, what's the point of finding a Reimann sum? It's not even accurate. Fair enough. So the question I want to pose to you now is how can we find a more accurate Reimann sum? So to do that, yes, we're going to think about this idea of the limits. That's how we spent so much time in the summer package and the first week of school talking about limits. So let me now once again draw my picture, y equals f of x. This time I'm going to say now delta x sub k represents the length, or you can say the width, okay? Or you can say the base of each subinterval. So from a to b, I'm going to have different subintervals. So perhaps here's my first one, a, okay? And then this distance here is delta x sub 1. Maybe the next one is wider. Whee! Right? This distance from here to there is delta x sub 2. Does that make sense? And then I'll draw one more. Maybe this is delta x sub 3, and so on. Okay? I mean, there's a whole bunch more. Dot, 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 dot. Now, the maximum of delta x sub k is the length of the largest subinterval. So out of the three that I've drawn, the maximum of delta x sub k is this interval length that I call delta x sub 2. That's the longest one, or the width of the fattest rectangle. Okay? Here's the thing. How can we get a more accurate feel for the area between the curves and the x-axis? You might be saying, hey, to be more accurate, we need more rectangles. Yeah. Make more rectangles and add them up. Really, you want how many? Almost like an infinite number of rectangles. Because if we had an infinite number of skinny rectangles, then if we add them all up, you pretty much get the area underneath the curve. So make more rectangles, infinite rectangles, with really small width. Which really means that this maximum delta sub k, the length of the largest subinterval, well, what you're just saying, if I want to be as small as possible, the maximum of delta x sub k really should be approaching the number 0. And that, my friends, is this idea of the limit. Okay? And so this notation here, the limit of the max of delta x sub k approaches 0 of the sum of k equals 1 to n of f of c sub k times delta x sub k, really represents now the sum of an infinite number of really skinny rectangles. Now, get ready for some nastiness, all right? Here's the concept. The area underneath the function from a to b is really then the limit of n approaching infinity. Now I'm saying n is the number of rectangles, right? I want the number of rectangles to approach infinity of the sum of this f of blah 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 times delta x. Now remember, in this case here, f of what's this, a plus delta kx. Okay, now let me try to explain that to you first. I'm going to draw a diagram here. I want you to do the same thing. Okay, once again, my same diagram. Y equals f of x, starting at a, ending at b. This time I'll have different, whoops, what happened there? This time I'll have different delta x sub 1s, right? Delta x sub 1. Maybe this is delta x sub 2. Delta x sub 3. And so on. Okay? By the way, if I want to draw this a little bit nicer, I'm going to use the right endpoints for all of these. Okay? Now, remember delta x? That's always the width, right? The width of each of these rectangles. The f of part is the height. Now, notice how I'm actually calculating the height. So for k equals to 1, that means my first rectangle. You'll see that this becomes f of the a value plus 1 delta x. So if I started at a and I went 1 delta x over, I'm actually at this point here. And can you see how this represents the right endpoint? So ultimately, I'm actually asking you to find the height at the right endpoint. Okay, that's what this notation here, a plus delta k, right, delta x times k, represents the height at the right endpoint. Okay. So, instead of writing delta x all the time, delta x is really the width of the subinterval. It's the difference between the length of the interval, b minus a, divided by the number of rectangles. So therefore, I made a replacement here, and I replaced delta x with all these things, b minus a over n. And that's where we get this expression, okay, which actually tells us the exact area underneath the graph. Okay. Now, I don't know if this is in the AB portion or not, but if we did use the left-hand heights instead, then the only thing that changes is this part here, where it's nearly no longer a plus delta k, sorry, a plus k times delta x. That is no longer the case. What I would need to do is modify this, and I want you to scratch this out. We're not going to add in a delta x, but we will add it in later on. So if you think about the first interval, I used a. It's the next rectangle that I have to add in one of these delta x's. So I'm going to use k minus 1 in front instead of k. And so in order for us to have a left-hand height, it's now f of a plus k minus 1 times now b minus a over n. Okay, so that helps us with the left endpoint. Okay. Now I know many of you are like, I'm scared. Don't worry, just keep following along. Okay. I want to show you how we can do example number 1 using both the right endpoint and the left endpoint, and you'll see something really cool happen at the end. Okay. But in order for us to do that, you're going to need a few formulas here, and that's why I wrote these here for you here. Okay, a few summation formulas. The sum of k equals 1 to n of 1. So this is really saying 1 plus 1 plus 1 plus 1 n times. Well, that's, of course, just equal to n. Okay. The next notation, the sum of k equals 1 to n of k, that means it's 1 plus 2 plus 3 plus 4 plus... Well, that's given by this formula, n times n plus 1 over 2. It's really Gauss and his formula that he used to find the sum of the first, like, 1,000 numbers. K squared, so this is where 1 squared plus 2 squared plus 3 squared and so on. That's this formula here. I won't explain it to you, it's just right there. And then finally 1 cubed, if we ever need to do that, plus 2 cubed, that's this. Why do I need to show this to you? Because that's going to help us do the next part. Okay. Now, don't freak out. There's going to be a lot of algebra work, but I want you to understand the concept, and in the end, I'm just going to use this final result to help us connect it to some other idea, and that other idea is the most important part of this lesson. Okay? So even though you might not get the work that I'm going to do now with this example, don't freak out. Just hang in there, follow along. Okay? So, I want you to find the area underneath the curve, y equals x squared plus 1, from 0 to 2, using a Riemann sum with an infinite number of rectangles. Okay? And in part A, it's the heights given by the right endpoint, and in part B, it's the heights given by the left endpoint. Those of you in the AB course, I don't think the left endpoint is there, but if you want to follow along, you're more than welcome to do so. Okay? So, let's see how we can actually attempt this problem here. So I told you that the area, the exact area, can be found by taking the limit as n approaches to infinity of the sum of k equals 1 to n of this f of c sub k, your heights multiplied by your width. I think the first thing we should do is actually figure out what the widths are. So delta kx in this case would be b, which is 2, minus a, which is 0 over n. So that's 2 over n. So plugging this in now, I'm going to say it's the limit of n approach to infinity, the sum of k equals to 1 to n, f of, and I'm going to use the expression a plus kx. So that'd be 0 plus k times delta x 2 over n. And then we'll multiply that by delta x sub k, which is 2 over n. So once again, this represented by a plus k times delta x because it's the right-hand endpoint. Okay. F of function, well in this case the function is x squared plus 1, so I'm going to rewrite this now as the limit n approach to infinity, sum of k equals to 1 to n. And I'm not going to use f notation anymore. I'm going to actually plug this in. So I'm going to plug in 2k over n. I'm going to square it plus 1. And that now represents the function, because of course my function is y equals x squared plus 1. Okay. I'd like you to now simplify this and expand, because we're going to have to calculate this limit. So the sum of k equals 1 to n. I'm going to expand this. This is 4k squared over n squared plus 1 times 2 over n. If I were to distribute this 2 over n in as well, you're going to hate this. You're going to have to write down limit n approach to infinity so many times, and this sum so many times, but so sorry. Welcome to life. You don't always get what you want. Okay. And so this expression represents the actual area, because I would say n approaches to infinity. We have lots and lots and lots of rectangles. Well, this is a limit, so we can actually distribute the sum and the limit into this thing. So I'm going to say the limit, actually I'm going to distribute the sum first. Let's do it one at a time. The summation is with the k, so anything without the k I'm going to actually take out and put it in front. So it's 8 over n cubed. The summation of k equals to 1 to n of k squared. And then distributing the summation in, once again, this is 2 over n. I'm just going to do that. This is the summation of k equals to 1 to n of the number, I guess it's just 1. And of course there's still a limit on that. Now, how is this particularly going to be useful for us? Well, here's where those formulas up top will come in handy. What is the sum of k equals to 1 to n of k squared? Well, that is just this expression here. Yes, ugly, but still doable. So n, I want you to write this down, okay? I'm going to replace it now with n plus 1, 2n plus 1, all over 6. Okay, that represents the sum of k squared. And then we have here the 2 over n, that stays the same, but the sum of k equals to 1 to n of 1, well, that just becomes the letter n. So now I'm going to replace that with n. Okay? Now, you're like, do I have to expand it out? No, we don't. Okay? So watch as I do this first, then I'll give you a chance to copy. The key trick here is to actually take the constants and keep them together, 8 over 6. And take this n and distribute it underneath. So notice I have n plus 1, 2n plus 1. I'm going to distribute the n cubed like this, n. Okay, and this other one here, that's just 2. Why is this helpful to me? Well, when I'm taking the limit as n approaches to infinity, notice that n over n here will just equal to the number 1. Right? Notice what I also have now is I have n plus 1 over n, and I also have 2n plus 1 over n, and this is all plus 2, still in the bracket. You're like, this doesn't look that helpful. Yes, it does. Do you know why? Because now when I apply the limit to this expression, the 8 over 6 can come out. And if I apply the limit to this expression, I'm just going to do it on the side right here. What is the limit as n approaches to infinity of n plus 1 over n? This is the n behavior model. Yes, you should be looking at the highest power of n's. In this case, n on the top, n on the bottom. So by the n behavior model, this is the same thing as the limit as n approaches to infinity of 1. Right? N over n, that's just 1. So the answer is 1. So this becomes 1 when I plug in the limit. This here becomes 2 when I plug in the limit. And we're multiplying that by 8 over 6, and I'm going to add 2 to it at the end. 8 over 6 is the same thing as 4 over 3. 4 over 3 plus 8 over 3? No, 6 over 3, right? So 4 over 3 here plus no, I'm sorry. I forgot to multiply that by 2. 8 times 2 is 16. 16 over 2 is the same thing as 8 over 3 plus 2. That makes more sense. And the final answer here is 14 over 3. So we actually found the actual number that represents the area under the curve from 0 to 2 using an infinite number of rectangles. In this case, right-hand rectangles. Now, for those of you in the BC class, yes, you do need to write this down. Those of you in AB class, don't worry about it, but you can if you want. Let me do the same thing now with the left-hand endpoint. And after that, I'm going to do one more thing on the next page, and then we get to the key point, okay? So just bear with me here. Okay, once again, I'm just going to do this as practice, because now it's the same idea. This time it's f of 0 plus not k, but k minus 1 to n. Okay, so this is the left hand, that's why it's k minus 1. I'm going to do the same type of work here at the beginning to help us simplify. I'm going to use the notation here, 2 over n times k minus 1 squared. Be careful with your brackets here, plus 1 times 2 over n. Keep doing some expansion. This becomes 4 over n squared. There's k squared minus 2k plus 1 plus 1 2 over n. What did I just touch? Not good. Limit n approach to infinity. Sum of k equals to 1 to infinity. 8 over n cubed times k squared minus 16 over n cubed times k plus 8 over n cubed plus 2 over n. So I just distribute this into all those things, okay? Don't forget distributing the 4n into these as well. Double check my work if you can, but I think I'm okay actually. Limit n approach to infinity. The sum of k equals to 1 to infinity. 8 over n cubed. And actually, I'm not going to do that. It's my fault. I'm going to actually factor it out now. 8 over n cubed. The sum of k equals to 1 to infinity of k squared. Minus 16 over n cubed. The sum of k equals 1 to infinity of k. Plus 8 over n cubed. Sum of k equals to 1 to infinity of 1. Plus 2 over n, sum of k equals to 1 to infinity of 1. Wow. And now we're going to make those substitutions of those formulas from above. And let's see what happens. Nasty algebra. 8 over n cubed. The substitution of n plus 1, 2n plus 1 all over 6, minus 16 over n cubed. That k just becomes n times n plus 1 over 2, plus 8 over n cubed, and that sum here equals to n. And finally, 2 over n, n. Wow. Now, how can we simplify this? Well, just like we did before, we want to put the constants together, 8 over 6 again. I'm going to distribute the n cubed amongst all 3 of those n's up top. 16 over 2 is 8. Okay. This would be 8 over n with an n plus 1 on the top and n like that on the bottom. This will just simplify to 8 over n squared, and this will simplify to 2. Now, as I take the limit and I distribute it in, once again, it's the n behavior model that happens. So notice I'll still get an 8 over 6 factor of 1, 1, and this becomes 2. Over here I get 8 over infinity. This is just 1 and 1. This is 8 over infinity squared. And notice then you have here 8 over 6 times 2, it's the same thing, that's 8 over 3. This becomes 0, this becomes 0, plus 2. Look at that. 8 over 3 plus 2. It's the same answer as part A. So it didn't really matter if we used the right endpoint or the left endpoint. As long as we were finding infinite number of rectangles, the answer is the same. I hope you thought that would be the case. And if you didn't, now you see it. You should be like, ooh, ah. And then now for the really big ooh and ah, can you move on to the next page? And I'm going to ask you, notice how you obtain the same answer with different choices of the heights. So in fact, once again, it doesn't matter what height you choose on a particular subinterval, you'll get the same answer as long as you're taking n approach to infinity. Now I'd like you to use your process of finding the definite integral, and can you now go ahead and calculate this for me? Because this is also supposed to represent the area underneath the curve, which is exactly the same as example number 1. Doing this, we're going to find the antiderivative, x cubed over 3. The antiderivative x is, sorry, 1 is x. We're going to evaluate this from x equals to 2 to x equal to 0. 2 cubed over 3 plus 2 minus 0 cubed over 3 plus 0. That's 8 over 3 plus 2. Well, you look at that. The exact same answer. So ultimately, what really is the limit of that Riemann sum? The limit of all those rectangles added together is actually equal to the definite integral from a to b of f of x dx. Definite integral. Okay. Oops, I think I was supposed to say this. The definite integral of f of x, there's no t there, for x equal to a, x equal to b, and that notation, of course, is this. Yeah, so definitely this equals to the integral from a to b of f of x dx. So the definite integral really is just the sum of an infinite number of really, really skinny rectangles. Okay? Now, how do Riemann sums with rectangle approximations connect now with the definite integral? That's what you need to do. So the concept here is that this definite integral is equal to the limit of an infinite Riemann sum. And this formula here is used for right-hand heights, but of course you can use left-hand heights as well. For the AP exam, yes, you will need to know how to write an infinite Riemann sum using the right-hand endpoints. I have never seen the left-hand endpoint questions because it produces the same answer anyways. But you need to know how to use the right-hand endpoints or heights and connect that to the definite integral and vice versa. So let me show you 2 examples, and then we'll call it quits for this one. I know this has been like the hardest and longest of all the supplements, but an important one because I wanted you to actually see how the 2 calculations give you the exact same answer. So here's example number 3. Let's take a look here. If I want you to rewrite this definite integral as a Riemann sum, the first thing you need to do is go delta x sub n, or delta x, and that's the difference, b minus a over n. So that's 3 over n. Okay. I would then go ahead and say this is equivalent to the limit as n approaches to infinity of the sum of k equals 1 to n of the function, and this is where I'm going to say I'm starting with the a value. My a value is 1 plus k times delta x. Delta x is just 3 over n. Okay, and then multiply that by 3 over n. So once again, if you're not too sure, because I used the right-hand point, this is this a plus k times delta x. Now I'm going to substitute in the actual function, that's x to the power of 5. So the answer that I'm looking for is really the limit as n approaches to infinity, k equals 1 to n, now use the 1 plus, I guess I'll write this as 3k over n. That's the x value. Raise it to the power of 5, because that's the function, and then multiply it by 3 over n. That is it. Done. Okay? Now I know for those of you in AB, you're like, what? The question was different. I know. So guess what? It's practice time for both classes. How would you actually go ahead and do this one here? Okay? So follow the same steps, and let's see if you get the same answer as me. And then we'll come back together to do example number 4. Starting in this case, the a value is 2. Replacing now with the function. Is this what you got? Don't forget the summation though, very important. If you did, bravo. Okay. Whew. Last one. Example number 4. Go the other way now. Write the limit of a sum back as a definite integral. Now the key thing here is to see, look, this 5 over n represents delta x. And look, that 2, that represents the a value. So if delta x equals to b minus a, which in this case is 2 over n, and that delta x is equal to 5 over n, I think now you can actually solve for b. So therefore b is equal to 7. Okay? Knowing that, what's my actual function? My function is something, this is your x, something to the power of 8. So if you thought, hey, is this as simple as saying the integral from 2 to 7 of whatever x I'm plugging in to the power of 8, and that delta x just becomes dx? Bravo. That's it. Okay? And so after this lesson, I do want you to practice with all of these exercises and check the website or Teams for the solutions. Okay? You need to practice all 10. Do that now before you forget.